Hi, today we're going to talk about why reactions happen the way they do and what factors affect the speed at which reactions happen. Understanding these basic principles of how reactions happen will really help you to understand kinetics. So what we're going to be talking about today is a theory that we call collision theory. So I want you to start off by thinking about a very simple reaction in which two molecules of HI react to form one molecule of H2 and one molecule of I2. We're going to keep coming back to this over and over. From the point of view of the physical location of each atom, what has to happen for this reaction to occur? Well, this hydrogen over here needs to form a bond with that hydrogen over there. This iodine needs to form a bond with that iodine. But for that to happen, we also need to break the existing bonds. In other words, the hydrogen can't create a bond to form a new molecule when it's still bonded to something in the old molecule. So we need to break bonds for a reaction to occur. And as you probably remember, breaking bonds takes energy. And it doesn't just take any random amount of energy. Each bond has a particular minimum amount of energy that you have to put in order to be able to break that bond. Now that certain amount of energy that it takes to make the reaction happen, that it takes to break the old bonds, that's what we call the activation energy. And that will vary from reaction to reaction, depending on what bonds are being broken. Now, where does the energy to break bonds come from in the first place? From collisions. So you can think about this in terms of car accidents. If you have a low speed collision, let's say you're going 5 miles an hour when you crash, you might just pop off the bumper of the car. But in order to really truly destroy a car and splinter it into a whole bunch of pieces, you need a higher speed, higher energy collision. So back to molecules. Collision theory tells us that the energy to break the bonds comes from the kinetic energy of the molecule. Basically, as the molecule moves around, its energy from its motion is transformed into the energy necessary to break bonds when that molecule collides with another molecule. And of course, they need to collide with enough speed that the bonds actually break. So, like our car accident example. But having the right speed is not enough. It also matters how the molecules hit each other. So for example, if I rotated our HI molecules so they're colliding differently, you can see that in this case, the hydrogens end up close together. They can form bonds, but the iodines can't bond because they're too far apart. So the collision really does have to happen this way that I showed you earlier, where the hydrogens and the iodines are both aligned. So in a nutshell, collision theory tells us that the speed at which a reaction goes is proportional to the number of effective collisions between reactant molecules that occur in a certain amount of time. Okay, so what's an effective collision? It's basically one that actually causes the reaction to happen. And for that, you need two things. You need reactants colliding with sufficient energy to break the old bonds, and also colliding at the right angle to form the new ones. Anything that affects whether they're hitting with sufficient energy or at the correct angle is going to affect the rate of the reaction, how fast those things are reacting. So one more thing before we dive into the factors that affect the speed of a reaction is a concept that you will hear about again in advanced chemistry, especially if you study organic chemistry. And this is the idea of a transition state. A transition state is a temporary arrangement of atoms with temporary bonds that occur during a reaction. Now these transition states only last a tiny fraction of a second, think nanoseconds, even picoseconds, so they're very, very short-lived. But it is very important to understand what these transition states might look like when we're thinking about reaction mechanisms, as we will do later on. So going back to our reaction, we are thinking about our molecules colliding. But let's think about how the bonds break and how the bonds form. So if we draw out the bonds as sticks, which is not what it really looks like in real life, at least we can see where the bonds are this way. As the reactants come closer together, as the electrons shuffle to new configurations, those old bonds are going to break and the new bonds are going to form. So the transition state is where the old bonds are partially broken and the new bonds are partially formed, but you don't have full-on bonds in either configuration. And then you go on to your products where you have the new bonds in and the old bonds completely gone. So again, the transition state is what happens in between where the old bonds are and where the new bonds are. Okay, so understanding those basics about collision theory helps us understand a number of factors that affect the speed of a reaction. And we are going to talk about 5 of those factors one by one. Factor number 1 is, what does your molecule look like? For example, what's your geometry like? If you have a molecule that's perfectly symmetrical, maybe it doesn't matter as much which direction your other reactant hits from. How strong are the bonds? If you have double bonds, those are harder to break than single bonds. So you would have a higher activation energy, which means it's harder to have effective collisions and you will have fewer of them. So the first thing is really just looking at the structure and geometry of your reactants. The second thing is, what state of matter are your reactants in? You probably noticed when you look at balanced chemical reactions that the majority of them have at least one reagent in the liquid, gas, or aqueous phase. And that's because in order for reactants to collide, they have to move around. Solids don't move around that much, whereas liquids and gases do. The third factor is concentration. And this is pretty much a probability thing, where if you just have a few molecules moving around, the odds of them actually colliding are pretty slim. But if you have a bunch of molecules all moving around, you're more likely to get an effective collision happening. So basically, the higher the concentration, the higher the probability that you will get effective collisions and thereby cause reactions. The fourth factor is temperature. Now, we've talked about temperature before, specifically the fact that it's a measure of the average kinetic energy of the system. And I've definitely shown you this graph before, where we have the kinetic energy on the x-axis and the number of molecules with that kinetic energy on the y-axis. And you remember, it looks like a Gaussian curve with an obvious average kinetic energy. Now, in this case, we will mark the activation energy on the graph, and it's clear that only a few molecules will have an energy greater than or equal to that activation energy. But at a higher temperature, which has a higher average kinetic energy, there are more molecules that have a kinetic energy greater than or equal to the activation energy. So the higher the temperature, the higher your average kinetic energy, and the more likely you are to have an effective collision. Our fifth and final factor is something that we call a catalyst. A catalyst is defined as something that allows reactants to interact more efficiently and therefore increases the rate of effective collisions. Now, there are 2 ways it can do this. One is by lowering the activation energy. But often what happens is that it makes it easier for something to hit the reactant at the correct angle. So one way you can think about that is by thinking about boxing. If you're in the ring, your goal might be to knock your opponent out. And in order to do that, you need to hit with enough energy to knock them out. You can't just go around gently tapping them. But of course, you also need to hit them in the right place. You don't generally knock someone out by punching them on the shoulder. So you've got to hit the right spot with the right energy, which may be hard because, of course, they're moving around and trying to dodge your blows. So most of your punches are not going to knock your opponent out. But now imagine that you're not in a boxing ring. Your goal is still to knock someone out, but you don't care to play fair. You're that neighborhood bully who's going to get one of your goons to grab your victim and hold them in place so they can't dodge your punch. And because the victim can't wiggle out of the way, you have a much better chance of hitting them in just the right place. So this is pretty much what a catalyst does, especially enzymes. If you look at how enzymes work, you'll see that there's an active site that holds the reactant molecule in a very specific position. And then there's no way for it to wiggle out of the correct configuration, so if anything hits it, it will hit from the right angle. So those are the 5 factors that affect how fast a reaction goes, and they all tie back into collision theory, which explains not only why molecules react, but why they react at certain speeds. I hope this was helpful, and I will see you again soon.